Very good afternoon, all. So, dear students, welcome back after the Diwali break, Dashera break. I hope now you have got refreshed and your energy is back and you got a good holiday. So, now let's continue discussions. We have already started talking about the graphs and we have already seen enormous applications of the graph in terms of social networking, etc. We have already talked. But one of the fantastic applications is Google Maps, I'll say, where you can easily see that nothing but effectively the graph of the cities and the connections or the roads is being used. So it is but obvious that it is a directed graph or undirected also can be there, cities and the connections, or I'll say roads between these. So cities effectively become the vertices and roads effectively becoming the edges. Of course, roads can be, if they are unidirectional or bidirectional, accordingly, edges can be directed or undirected, but ultimately, it's a graph of vertices and edges. And another thing is, in case of a Google map, you are now very frequently using it while traveling, and you come to know how much distance you have to travel, how much time you will take, and etc. etc. Effectively meaning that the edges, now in this case, the edges are effectively weighted edges. Each edge, for example, the distance is stored as an edge, or distance is stored as a weight, corresponding weight for the edge. So now distance remains fixed, so I can always store it. So if I say city A, if I have city B, and if I say this city has 105 kilometers distance, city B to city C, let's say 35 kilometer. So one way of going A to C can be via A, B, C. So I can easily find that it will require 140 kilometers. And other way could be, for example, I have here A to D, which takes 50, D to E, which takes another 30, and which takes this one another 40. So I could say AC I can reach via A, B, E, C. Effectively, this becoming 50 plus 30 plus 40, that is 120. So I could find that this is lesser distance, smaller distance, and this is how the routes are calculated. So distance is an obvious weight being considered for the edges, but nowadays Google Map also tells the time taken to reach. And in fact, this time can be dynamic because in the morning time or in early morning versus peak hours, all timing will differ. Peak hours, the timing will be different as we know, and accordingly, not only peak hours, based on the traffic condition, based on the road quality. So all those things do come into picture, and accordingly, we get all these things calculated. Road quality, then corresponding, traffic intensity, or holidays, or weekend or weekdays, etc., etc. All these things make a difference and then can affect the time. So I cannot say that time is a predefined. On the other hand, distance is more or less predefined. So we can easily see the Google Map must be using very complex algorithms, of course, lot of inputs, lot of storage, and then maybe machine learning also coming into picture, doing all that. Then your speed of driving also coming into picture. So many inputs, so many parameters, speed of the driving, all that will also come into picture. But well, that becomes a very advanced and difficult situation to discuss and handle in a small algorithm. But ultimately, it all means graph and its paths are going to be really computed. Paths, effectively, I mean sequence of edges or set of edges. So I can easily see if I travel multiple edges one after the other, it will become path. For example, AC is one path. It could be ABC as one, or it could be ADEC as another. So both are two paths consisting of multiple edges. Ultimately, we need to work over paths and many such connections. So today, we are going to consider graph as a weighted graph now. So we are going to consider it as a weighted graph. And a weighted graph effectively means that edges have weights. So whenever edges have weights, not just their presence being used, then we call it a weighted graph. And using weights, many decisions will be taken. So for today's discussion, we assume undirected graph and connected graph. And why we are assuming all these for the today's discussion is because from such a graph, weighted, undirected, and corrected, ultimately, I am going to find out certain special characteristics, which is known as minimum spanning tree, which can be an excellent tool to solve many problems, including finding the minimum time for certain routes, minimum educational examination duration, minimum set of people who can do a work within stipulated days, etc., etc. So we will systematically go. First of all, I will define what is a spanning graph. So I know what is a graph. Then I say there is a spanning graph. So if I have a graph G, then I say spanning graph G dash is a minimal subgraph such that it has all vertices and they are connected. So they should remain connected. So minimal means we should use less number of edges. All edges are not desirable. And I say I need the vertices all to be there and connected. They should remain connected. No vertex should become unconnected. Initially, graph is connected. In the spanning graph also, it should remain connected. Then from spanning graph, I define a spanning tree. And a spanning tree means the spanning graph G dash should have no cycles. Effectively meaning that it will have precisely, if there are n vertices, then for making it a connected and minimal tree, it will exactly require n minus 1 edges. I can easily say why. Even if I have, let's say, undirected graph. So I say, let's assume all of them being considered as outgoing or incoming edges. So let's say I'm considering something as an outgoing edge. So maybe I say this is each of them as outgoing. Somewhere they are connected, somewhere they are connected like this. Then I say any vertex taken, let's say this is A, B, C, D, E, F. Say one of them, if it is a tree, one of them will become root. So root, let's say D or anyone becomes, it will have no incoming edge. If I consider all edges as incoming, then I'll say no incoming, but all other vertices are definitely to be covered. So no incoming edge will exist for this. And for all vertices in spanning tree, each vertex will require exactly one incoming edge. And then only it will become a spanning tree, or it will become a tree of all vertices and minimum edges. So exactly, except for root, all other vertices will require one and exactly one edge. So exactly n minus 1 edges in total. Hence, I say this becomes a spanning tree. Then what is more important to us is minimum spanning tree. So what is a minimum spanning tree? Minimum spanning tree means spanning tree with least cost or least cost, where cost effectively cost of the total MST, where cost means nothing but summation of all weights or summation of weights of all edges in the MST. So MST has effectively n minus 1 edges. Effectively, it means if I say I equal to 1 to n minus 1, weight of edge I, all these edges to be summed together will become the cost. And I want the spanning tree to have least cost of the total MST. So that means from a graph, many spanning trees will be possible by considering many different edges. Many spanning trees are possible because ultimately what I need is all vertices and all vertices connected. But minimum MST will be unique and MST will be always having, or I'll say MST will always have the minimum cost, and there can be more than one unique MST. Like, for example, if I say I have here A, I have here B, I have here C, I have here D, I have all these connections. So, of course, this also becomes one MST. Say A, B, C, D. So this is this, I'll say this becomes one spanning tree. Might not be minimum. So this is one spanning tree. Other spanning tree could be I go A, B, C, D. This can be ST2. Similarly, I can have A like this, like this. This is spanning tree 3 and many more like that. All these can exist. So MST will have the minimum cost. So MST will mean minimum weights, minimum cost, total cost. And of course, we can find this can have variety of applications so that I know that all vertices get covered and they get covered in minimum time. For example, I say that I want to travel all cities and in a way that I should reach each city exactly once, and once I am going there, I would like to travel with minimum distance to be covered. So maybe I'm willing to find out the minimum spanning tree for this. So this is one of the fantastic algorithm which is needed and in many situations. So to solve MST, effectively there are two algorithms. One is known as a Kruskal's algo by the name of the person who designed the scientist, and other one is known as Prim's algo, again with the name of the other scientist who has designed. Of course, both will produce MST. So produced output or produced MST will have definitely the minimum. That means will have the same cost because both are minimum. Although both may produce a different MST edges, and even with the same algo also multiple different options are there because edges can have duplicate weights. Many edges can have same weight. So of course there can be many choices, and that can be one way that some edges may get chosen in one, some other may get chosen in some other. So set of edges in MST, set of edges may differ, but a total cost will never. Set of edges may differ with one or other solution, but total cost will never. Hence, that will become an MST, will never differ. So this is what we are going to see now. So I say, now we are going to talk one by one both algos. So today we are going to talk of Kruskal's and algos and Prim's algos working. And next class, we will see the programming of this. So let's go one by one. Kruskal's algo. This says that effectively, my final, I'll say my answer will be always generated as a set. So I say answer set will come as an answer. Initially, it will contain set of all or so I say answer set is effectively having set of vertices where I say each vertex being considered as one connected component, as a distinct component. So component, of course, many vertices may be connected with each other, so they will become single or more component. As SCC, we have used the word component. So I say Kruskal algo is mathematically, we are going to understand that mathematically set will be used. Of course, a set we have not used or we have not implemented. So set implementation can be in multiple ways, implemented via, or I'll say sets are implemented using the concept of implementation can be done using concept of disjoint sets and forests, and there are a variety of applications and implementations. All those you are going to study in the next semester as an advanced data structure course also. But there are in the book also in detail it is given. So one chapter is already there. If those who are willing, they can start studying in advance also. So disjoint sets can be implemented using some linked list or maybe some arrays, etc. But in case of a disjoint sets, obviously we need a faster operations to do union, intersection, membership, and hence we have to be very careful to choose the suitable data structure because these operations will be very frequently needed. So for the time being, we are not bothered about the implementation. Let's go Kruskal algo's implementation to be discussed later. But for the time being, understand, assuming or mathematical understanding we will develop, assuming the sets being discussed. So I say, effectively, initially I have my answer set to have various sets or various individual components, various vertices. So I say A, B, C are all vertices and all of them as an initial set. Then, of course, n-1 times I will repeat and I will say add a safe edge. Now, here the word safe edge. And during your lots of interviews, etc., the word safe edge is going to be discussed, and you should know that this is a conventional special word which will be referred by the interviewer or which will be asked to you from many people. So you should remember that the word safe edge means a specific meaning. So what is a safe edge? A safe edge means it's a least weight edge. In case of a Kruskal algo, the safe edge will have a slightly different meaning. In case of Prim's, it will be a different. So it is said to be a least weight edge that connects two distinct components of answer set. So two components of answer set will be connected via this. And of course, after connection, both components will become a single component. So both components will come in the same set because they are connected component now. It will be more clear once we see an example and discuss. So, but this, if you remember that every time we have to just add a safe edge to set A, and in a way that it is a least weight edge that connects two components of answer set. This explains effectively everything and a least weight. Let's take an example. It will be clear from this graph. So I say, this is the graph which I am using. Let me have now a different pen color so that when I discuss, I am able to show you in a different manner. So initially I say my answer set is having a separately as a one set, B as another set, and so on. So up to all, say up to I. So all these are there. Now, first time I have to add a least weight edge. So least weight edge at present is this one. This will get added, obviously, and it connects H and G. So effectively that becomes that I have a GH as one component now and all others as they were. GH becomes one component and this edge gets added here. And because it is a least weight, so I am going to use. Effectively, indirectly meaning after this, I will need the next least weight. So next week I have the next least weight is a 2. I have two choices. Yeah, anyone can be added. Let's assume that if they are not leading to a cycle only, then they will be added. And when it will be a cycle, it will be just clear after some discussion. Let's assume we select this one. This selection will mean I and C will get connected. So earlier I had GH as a single component. Now I and C as another component and all other vertices are alone. After this, again, next least weight edge to be selected. Now, of course, now you can easily see every time we need vertices in the order of ascending weights. So effectively, sorted edges will be desirable during programming. Sorted edges will be desirable. So we will require this every stage. Now let's assume GF. So this can be selected because GH is one set, one component, F is a separate component. So I can select this GFH. So now this set becomes modified and instead of a GH, this will become GFH and IC and others. The point worth mentioning here is now that let's assume if I have let's assume if I have, let's say another vertex like this without direction, of course. So I have this vertex like this, and let's assume this is also weighted 2. Next time, when I have GFH and I'm trying to have another vertex to be added, then now the situation will come, and let me put the color also correctly so that I can discuss again. So now I say this is the next least weight edge, but it is connecting H and F. H and F are in the same component. Distinct components are not being connected via this, hence this will not get selected. So at present I have GFH, IC and all individual vertices. All individual vertices are remaining here already there. So effectively after this, I will look for the next least weight edge. This is a 4. So this will mean that now my individual vertices out of those A and B will get connected and they will become one component. After this, I have, let's say, this one, C and F. If they are in a different component, C is there, but F is not there. So C and F will be connected and this will be selected. Now C is this component, F is this component. It means both of them will get combined now as a component GFHIC. And if you see clearly, carefully, if you see GHFIC are as a connected component. For example, I can go like this, like this. This is connected, but no cycle. If IH gets connected, then this will become a cycle. So this can become a cycle, and you can see because I and H are in the same component, IH should never be added, otherwise this will lead to a cycle. So similarly, after this connected now, next time another vertex with anyone with 4 if available, not available, then 5, no, so I have next one to be this one, 6. Now 6 is connecting G and I. G and I are in the same component. Two distinct components are not getting added, so it will not get connected. So now you can see you have one connected component here, second connected component here. Both are presently unconnected, but at some stage, these two will also get connected and they will become a single component. Slowly, all of them will get connected and all will come into a single component. So single component will come later. Similarly, all others will also get connected. And finally, we will have one component of all n vertices. And that will exactly mean one component will come ultimately of n minus 1 vertices. Oh, sorry, n vertices, not n minus 1, exactly n vertices. How? For example, after this, so GI cannot be calculated, then 7, this cannot be there. CD. CD are not connected, so I will get a D also added here. And once a D added, so this is also done. After this, the next least weight is BC. BC or AH, these are there. So can I have a BC? Yes. So now these two connected components will come, as we have already seen that edge BC will add. So once edge BC comes into picture, BC will mean edge with weight 8 coming here, and that will effectively mean this component becomes GFHICDAB. So up to this, I have now this plus remaining components. Total vertices are 1, 2, 3, 4, 5, 6, 7, 8, 9. 9. And at present, we have 3, 3, 6, 2, 8. 1 is still remaining. So after 7, 8 will be tried. Can I have AB? Can I have AH? A and H are in the same, so no. After this, can I have C? I can easily see E has not been included. So ultimately, then vertices with 9 weight and 9 weight, I have this DE. D is here. E is here currently as a separate component. And then finally, this DE gets selected. And this selection will mean plus DE edge to be added. DE edge added will ultimately make this set as GFHICDABE. Remember, it's a set, so ordering doesn't matter. Unordered set by default. So whether you write it as A to I or this order doesn't matter. It's a set. But this is how this becomes a minimum spanning tree. So Kruskal's algo used this process, and I'm able to have the same graph done like this. So based on this, let me just, I'll need this graph again to discuss the Prim's algo. So I will just save this file with a new name so that I can use this as T2. And later I will combine all these. So I will just have this T2, and let me just stop this and go to my other file where I have got this particular graph available again. So I'll resume from here, and let's say then we will go to the new algo, and here I will now again go for the Prim's algo. So now we talk of a Prim's algo, and very similar to Kruskal, but here the processing will be different. In this case, again, I will say answer set will be there definitely, but answer set in this case is going to have always forming a single tree. At all stages, it will always be a tree in all situations, at all stages. So that's where it differs. Means what? Here, we will start with any vertex, with a vertex, with a start vertex, and start vertex can be any vertex. You might be probably confused that why any vertex will be okay. The answer is yes, ultimately that vertex also has to come into the answer set. and that vertex will only come via its edges only. So some edge connecting that vertex, like in the recent E edge was connected with a higher weight, but ultimately E has to reach, and E's connectivity is via 9 weight only. So that will come. Here also similar concept will happen. So start with this some vertex, and it is in answer set. So at that answer set has only one vertex, that is a root. Each time, so n minus times, n minus 1 times, I am going to add. But now what I am going to add a safe edge. Of course, a safe edge. But what is a safe edge now? A least weight edge. Obviously, least weight edge is must, least weight is must. But now the least weight edge will be connecting the answer set tree, because answer set is a tree effectively. So I'll say this will connect answer set tree to a vertex which is presently not in the tree. So every time the safe edge will mean a least weight edge, but the edge in a way that a new vertex gets added to this particular tree or answer set. So that means at no time it will have two distinct unconnected components. For example, let's continue with the same discussion, and let me have the pen changed here, and then I'll talk of the Prim's algo. Let me have a different pen now. Say I'll take green pen, and then I'll use this for Prim's algo. So for Prim's algo, initially let's assume we select an E itself. So my answer set, intentionally I'm starting with E so that you get a proof that come what may, still we will get the correct MST. Now from E, ultimately step 1, I have to add an edge. Add safe edge. But safe edge now doesn't mean the least weight edge of full graph. It means least weight edge which connects E to someone. So it means E to another uncovered vertex is to be added. And that should be least weight. So effectively that means that what I am going to add is something like this. Something like this to be added. Of course, now I can see E has the two choices. From E, I can always go either this side, which is the least weight, obviously, or I had the other, which is not least weight. So through this process, this gets selected and my answer set becomes ED. So ED is selected. Then from ED, next time, now I have to add an edge which connects ED, this particular tree, with another vertex. So obviously, either I can go via E, say this one, or I can go via D. From D also, I have two routes, but out of this least needed, so either I have via D to go this side, or via E to go this side. So effectively, from every covered vertex, I will need to know uncovered minimum weight connections. That will be probably some kind of a min heap data structure useful to me in tomorrow's implementation. So I say from that viewpoint, I'm going to cover this, and I see now DC can be covered, and this will add to this. So I will have now EDC being my answer set finally. Here is my marker. Yeah. So EDC becomes my answer set. From this again now via C, I have the outgoing connections, or I have the possibility either to go this side. Others are more than 2. So obviously from C, if I travel from C, this could be the best choice. But I am not supposed to only look at C. I am also supposed to look via D also. I can lead to a new vertex. This can be one way. Via E also I can need one vertex. This can be another way, and this is another choice. So obviously Ci is the least weight. So Ci will get connected, and I will say now I got some more connection. So Ci got connected. After this, now from I, the choice can be this side to be the best. This is already covered, so not this choice. From C, the second available choice can be this one to be the best choice. From D, already I have this one to be the choice. From E, I have this one to be the choice. So from C, obviously I have a better connection compared to I or D or E. Then I will say, go for selecting this one. So this one I will select, and then I have got F connected. From F, now again I will say, now via F, the connection could be either this one is already covered. So from C, the other possibility now gets added is this one. So whether this one to be done or the C's connection is already over. So C's connection, this one to be done or not, E's connection, this one to be done or not. Out of all these choices, this becomes the best choice. So now I will have FG added. So I'll say FG gets added. You can still see every time it is a connected component. Say, for example, this I started, I'm able to go like this, like this, like this, and then maybe backtrack and like this, and then like this. But all these are connected and no cycle exists. So from say this side, then this side, then this. Similarly, from G, now I can easily see this one will be the best choice to connect. So I will have GH connected. And now you can easily see this vertex, this edge also ultimately came, this edge ultimately came, this edge also ultimately came, and continue like this. So effectively this came. After this, again, I have effectively the 7 covered. Similarly, the next step, step 8 will come. And step 8 will mean that the correspondingly maybe B or A will get added through the suitable connection. And finally, the remaining step 9 will come. Or I'll say rather to be saying step 7 because n-1 steps needed. And then step 8 will come. The remaining vertex, the remaining last vertex will get added. So last vertex will get added. So this is the way Prim's algo works. So you can see in Prim's algo, we didn't require sorted edges. All edges were not required, hence we need not go for this. And we can definitely avoid that, not needed. Only selected edges, and out of that least weight needed. In Kruskal, it was needed and processed like that. Some edges were rejected because they were leading to cycle, but we have to go edge-wise, sorted-wise. Here, we are going the covered vertices and their connections. Covered vertices, connections, least weight. So I say covered vertices, connection, and least weight. So for each vertex, probably I can have a kind of a min heap. For each vertex, I can have a min heap kind of a thing through which the heap priority or the priority will be based on the connections with the least weight. So that will be the probably the logic for implementation. So for each vertex, we will target something like this and programming will be done. So next class, we are going to do the programming and we will understand those programming in the coming class. But before that, I must tell you that must be clear that Kruskal's versus Prim's algo are different. In Kruskal, unconnected components exist in the answer set and they get connected later at some stage. In Prim's algo, all components are going in a way that every time tree remains there, every time connectivity remains there, we start with a single vertex, and every time one uncovered vertex is added through a certain edge, and edge has to be least weight. So this is the way both will be used. Read this, understand it clearly, and then next class we will do the implementation. Bye bye. All